video, we will give an introduction to the programming language C, specifically meant for students of the course Computer Architecture and System Software. The main goal of this video and this exercise session is to give you a broad knowledge of C, enough so that you can translate C to machine code. On the exam, we will not evaluate you on your knowledge of C. Instead, you will get exercises on which you have to translate C code to machine code. The goal of this session is to teach you enough C in order for you to be ready to translate C code to machine code. The goal is not to make you a fully fledged C programmer. Let us start by discussing a simple hello world program. So in C, execution always starts in the main function. First line of code that will be executed for this program is line 4, the printf statement. In this case, printf will print the message hello world to the standard output, which is typically displayed in your terminal. Next, we return 0 as a result of this main function. The main function can take a return value, an int, as specified and in the signature of the method. The int that is returned is basically a status code. If you return 0, you're telling your system that your program has executed successfully. You can return, for example, -1 here as an indication that something went wrong during execution. And you can use different integers values for different status codes. Return 0 means my program ended correctly. The last thing we have to discuss about this file is the include statement. This is the way we include a library in C. In this case, we include the standard input-output library, standard IO. And in this library, the definition of the function printf is defined. So thanks to this inclusion statement, we can print f. Now let us see how we can compile and execute this program. So first, you open the terminal and you go to the folder of your hello world file. In this case, it's CASS C. Here's the hello world file. And now, so we have to manually compile C programs, meaning we translate the C program using a compiler to machine language to an executable format that our PC can understand. To do this, we use the program GCC in this course. So you type GCC, the file that you want to compile, then -o to say you're going to specify the output file. And in this case, let's call it hello world, our output program. If I now ls, you see there is a new file here, hello world. This is an executable file, hello world. This is an executable file generated by GCC. And if I execute this file, then I get the result of my program. So that's a simple hello world in C. Now let's increase the complexity. So in this simple program, we define an integer, we give it the value 5, and then the next line we print the value of that integer. Now C uses a format for printing called format strings. You might recognize it from Python or you might not, it has a similar system. You use placeholders in your literal string, and those placeholders get filled in by the values that you specify as extra arguments to the function. You can look up format strings in detail to figure out how they work. So this line of code prints the value of I. Now, in the next line, we print again, but now we don't print the value of I, we print the address of I. So this is something what makes C special, different from most languages. C is a very low-level language, and it works directly with memory addresses. So every program is being executed in its own virtual address space, and all of your variables are located somewhere in your memory. They're located somewhere, and they also have an address, a virtual address. This virtual address you can access with C, and we will actually use that a lot. So how do you access the virtual address of a variable in your program? You do this by the ampersand operator. So ignore this part for now, we will get back to that. The ampersand operator before your variable name denotes the fact that you want the address of the variable instead of the variable. So this will resolve to the address of the variable of I. And if we want to print an address in C, we use the %p placeholder in the format string. So what this program will do is it will print I, the value of I, and the address of I. And then it will return 0, denoting that the execution was successful. Let's compile this program. Integers.c, let's call it integers. Again, we have our... And what we see is we get value of I, 5, address of I, we get a hexadecimal value, and this is an address in our memory. Let's take a look at memory in a visual way. So every byte in our memory, in our virtual address space, will have a unique address. So byte 0 will have address, or byte 1 will have address 0, byte 2 will have address 1, and so forth. We make a decision not to give every single bit in our memory an address, because then we would have 8 times as many addresses, and they're not necessarily that useful. If you have an address for every byte, that's already enough. Now, let's say we declare an integer, and an integer is 4 bytes in size. It depends a bit on your machine, but on a lot of machines, an integer in C will be compiled to a size of 4 bytes. So, an integer, 4 bytes in size. If we store that somewhere in memory, it will have an address. But it will also comprise of 4 bytes. So basically at 4 different addresses, we will find a part of the integer value, right? So let's say we declare the value 5. In this case, the value 5 will be stored at the addresses E4, E5, E6, and E7. And then the next word, the next value will be at E8. So as you can see, one integer here, it's 4 bytes in size. Why? On a 32-bit machine, typically your registers are 32 bits or 4 bytes in size as well. So values are often multiples of 4 bytes. Many variables will be multiples in size of this 4 bytes. So we have an address space here. We have a bunch of addresses, and typically this is visualized with increments of 4 because values often have sizes of 4 bytes or multiples of that. We will see exceptions to this as well. In the previous example, we saw that every variable has an address associated with it. Now, you might wonder, can we also store this address in another variable if we want to do calculations with it, if we want to save it? And the answer is, of course, yes, we can do this. We can store an address of a different variable. We can store an address in general inside of a variable. And that's what we call a pointer. So a pointer is also a variable which stores the address of a different variable. Great, let's take a look at the code. This example declares an integer, and this integer has a value 5. Same thing as in last example. The next line here defines a pointer j. So to do this, we use this star attached to the name of the variable. This denotes the fact that j is not an integer. No, j is a pointer to an integer. So the value of j is not an integer. The value of j is a memory address. And that's why what we store in there is not I, but is %I. It's the address of I. Great. Then we declare a variable k here. This is an int, a regular integer. We don't attach a star to it, so it's a regular integer. It's not a pointer. And what we do then is we store the value of the address located in J into K. So let me say that again. So J as an address, as the value of J is an address because J is a pointer. Now we dereference this pointer, that's what this is called. We follow the pointer and we go look at the actual value. Let's say I would have written int K is J. Well, you want to assign an address to an integer. That would give an error, first and foremost. Your compiler would complain because you're assigning an address to an integer. But what do we want to do here? Well, obviously we want to save the value of I into K, right? J as the address of I, and we could write int K as I, and then we would save the value 5 in K. But now we want to use the pointer to I. The pointer to I is, in this case, is J. And we want to use not the address, but we want to use the value at the address that is stored in J. So to get the value at the address stored in J, we use a dereference operator, which is again the star. So we type star J. In K, the value of I will be stored, or the value of the address in J. This is important. Repeat this. Make sure that you understand this. This is very, very important to understand C. Understand the fact that you can work with addresses, you can store addresses in variables called pointers, and you can dereference pointers by using the star operator. Also, notice that the star operator is a bit overloaded in the C syntax. It's being used in two different contexts. First, it's used in a data type declaration. You're saying that J is a pointer instead of a regular integer. And next, it's also used as a dereference operator. It had two different uses, both related to addressing. It's a bad design choice of the language designers of C, but we have to deal with this. Great, let's look at the print statements here. So this first print statement will just print the value of I, which should be 5. The second print statement will print the address of I, right? Ampersand I. And we use the P placeholder again to denote the fact that we're printing an address. This will print this value in hexadecimal. Now, the next line, we print the value of J. Now, the value of J, you might pause the video for a second and think about what type of value should be printed here. Is it an integer value or an address? And the answer is, of course, that the value of J is an address because we store the address of I in J. So that's why we use %p here to print the value of J, since J stores an address. But in the line after that, we print the address of J. So J is a variable, so it also has its own address, right? J stores the address of I, but it also has an address itself. And that's what we print in line 10. Line 11, we print the value of K. You might pause the video again, see if you can figure out what this should print, what is going to be printed here in line 11. And the answer is obviously the value 5, since we've dereferenced J, which is a pointer to I, meaning we store the value in I, meaning we store the value 5. So the value of K will be 5. The address of K is printed in line 12. Now let's see this in action. GCC pointers.c. Let's call this again pointers. And let's execute this program. Value of I is 5, as expected. Address of I is an address in memory. The value of J is equal to the address of I, because that's what this line does. And then the value of the address of J is a different address. It's close to the address of I, but it's not the same address. It's located a little bit later in memory. It has a little bit higher of an address. And then the value of k is 5 and the address of k is ends here with AC. Now, this is a 64-bit machine, so it's a little bit different than the addresses from the slides. Using the slides, we're now going to do a small self-test. After each question, I suggest you pause the video and you think for yourself if you know the answer or not. You should be able to answer all of these questions. If not, maybe rewind or look into different sources, but you need to understand these concepts now. Great. So, first of all, what we see here, what is the question, what changes in memory? We have our program, the same program as we just discussed. And then we're going to set k to 3. Now the question is, this memory on the right, this is an illustration of what the memory will look like after executing the first few lines up until this point of initial memory. What we have is a variable I stored at the address ending in 78 with the value 5, a variable k stored at 7c with the value 5, and then a variable j, address ending in 80, and it stores the address of I, which you can see. So the value of j is the address of I. J is a pointer to I. Great. What now happens if we set k to 3? This is an easy question. What changes in memory? Pause the video. What changes in memory is, of course, that the value 5 here is going to change to 3. Exactly what happens. Now let's make it a little bit more difficult. What happens if we set j to 9? Pause the video. So again, the same thing will happen. The value 9 will be stored at the address of the variable j. But this is not a good thing to do. So what we did was we assigned a value, an integer value. We assigned that to a pointer, which is expecting an address value. Now, you can interpret an integer as an address. This would be address 9, but you probably do not have any idea what is located on your machine at address 9. And you definitely don't want to mess with it, because you might crash your computer. Luckily, you won't be able to mess with it. That's a different story, but your computer is secured. In any case, you don't want to do this. J is a pointer. Don't assign manually an integer value to that, because now j points to the address 9. Your compiler will warn you about this. Don't ignore your compiler warnings. Read them. Alright. Next question. What changes in memory when we set j to this? I'm not going to give more hints. Pause your video. Of course, what changes in memory is, well, %k means the address of k, so we're going to assign the address of k, which ends in 7c. This address, we're going to assign that to j, and so now j is a pointer to k instead of to I. Since we actually store an address here, this is perfectly fine. Last question. What changes in memory? Well, this is again a small difference. We could star j equals 9. What is going to happen now? Pause your video. Well, what will happen? This is our dereference operator. We will follow the arrow. We will follow the address stored in j. J stores the address of I. We will follow that address, and at this location we will store 9, meaning 9 will be stored at the variable I, that location. And that's what happens. Writing star j is the same as writing I, since j points to I. We dereference j. At this point, you hopefully have an understanding of how pointers work, how you can use the address operator, how you can use the dereference operator, the star, and how you can declare a pointer as well. So once you know how pointers work, let's take a little bit deeper look into data types in C. So here's a bunch of data types, and we're going to print the amount of bytes that is being used to store each of these data types in memory. So In the first line here, we will print the bytes that are in a char. Now, what's a char? A char stores a single character, a single letter or number, a single character from the ASCII table. Next line, we print the bytes in a char star, which is a pointer to a char. A pointer to a char is always a memory address, so the size of this is the size of a memory address. Then we print the amount of bytes in an integer. We print the amount of bytes in an unsigned integer, an integer that cannot be negative. Then we print the amount of bytes in a long. We print the amount of bytes in an unsigned long. Again, can't be negative, can only be positive or 0. Then we print the amount of bytes in a floating point number and the amount of bytes in a double. This size of operator, as you can tell by this illustration, simply tells us how many bytes its argument will need, how much space it requires in memory. Alright, let's take a look at this, the execution. And this is machine specific. This is not necessarily the same on your machine. It depends on many different factors. For example, whether or not you have a 32-bit or a 64-bit machine. So that's why we need to use the size of operator, and we cannot use hard-coded values here. It's not necessarily the case that an integer is 4 bytes on every machine. For example, gcc size of.c o size of. Let's run. And as you can see, on my machine, and on every machine, this is the same for every single machine, you can rely on that, a char is 1 byte in size. This is an exception compared to most data types. Most data types are multiples of 4, but chars only take 1 byte. Why? Because if we want to store text, we don't need more than 1 byte to store most characters, and it would be a big waste to reserve 4 bytes to store one single character. So on my 64-bit machine, an address is 8 bytes in size. Now, on a 32-bit machine, you couldn't have an address of 8 bytes because then you would need 2 registers to store a single address, which would be very efficient for hardware, inefficient for hardware. On a 32-bit machine, you would get the result 4 here. The fact that you use 4 bytes, 32 bits, the size of one register to store an address. And every single address will be this. So if we write an address of an integer or the address of a float, of course, an address is an address. Doesn't matter for which data type. It's just an address. It's 64 bits on my machine. Then on my machine, an integer is 4 bytes in size. An unsigned integer is the same size. The only difference between an integer and an unsigned integer is the way that the bit representation is interpreted. So in a typical int, a regular int, the first bit of your integer will be used to denote the sign, negative or positive, and all the other bits will be used to store the actual value. While in an unsigned integer, the first bit is also used as the value, since we already know it's positive. That means you have double the amount of positive values you can store. The same goes for long and unsigned long. Then we have 4 bytes to store a float on my machine and 8 bytes to store a double. We've discussed pointers and we discussed data types. So now we are ready to tackle arrays in C. So as you know, an array is a list of values. Now, an array, in some languages, arrays might be able to change in size or do fancy stuff. In C, all an array is a collection of values of the same type. And importantly, the size of an array will never change. Once you define an array, you define how many elements are in that array, and that will never change. Now, what is an array in C? It's very, very simple. It's simply a collection of the values of the same type. So for example, 5 integers. And what C will do for you is it will reserve enough space in memory to store all of those values, and it will do this in one consecutive piece of memory. So if your integer is 4 bytes in size, and you ask for an array of 5 integers, what will C do? It will give you 20 bytes of memory, and it will return in your variable the address of that first byte of those 20. So that brings us to the first line of code in the main function. We declare a C array. This is a syntax. You define the data type of the array, of the values of the array. Then you do the name of the array. And then you put these brackets here to denote the fact that you're going to define an array. I don't like a syntax, but we can change it. So next, we can initialize this array in this fashion. There's other ways as well. And so what this does is this creates an array of 5 values. The size will always be fixed. Great. That's what being printed in the very next statement is the address of the array. And notice that we don't use the address operator here. We don't need to, since an array always is a pointer. So once you declare an array, this array will always be a pointer to the first value in your array. This is a pointer that cannot be changed. So you cannot change the value of this pointer to something different. Then you get error messages. This R will always point to the first value of the array, but it's already a pointer, and you can use this as such. It contains the address of a first value. So that's what's being printed here. That's why we don't need to put the address operator again. Now, what happens in the rest of this code? Well, in these 2 lines of code, we're going to iterate over the array. And in this for loop, we use a nice trick. So we know the size of the array is 20 bytes, and we know the size of an integer is 4 bytes. So if we divide those, then we get the amount of elements in the array. This is the way to dynamically write a for loop where you don't know how many elements are in the array. If I put a 6th element here, this will still work, right? This is simply a way to calculate the amount of elements in an array. You divide the size of the array by the size of the data type of the array. This for loop will thus iterate over all values of the array, and we print in this for loop, we print the values of the arrays. And next we will print all of the addresses of the values. So now we do use the ampersand operator. So once you dereference an array by using these brackets and an index, this is replaced not by an address but by a value. So R is an address, the address of the first element, and using these brackets you will access the actual values behind those addresses. So if you do R0 here between the brackets, then you will access the value stored in R. If you will use R1, you will access the value stored at memory address R plus 4, because an int is 4 in size. So these addresses will be printed here. And then lastly, we will print the size of int, the size of an R. So let's take a look at this code being executed. What we see here, the address of our array, this is the address. And what we see is that the address of our first element is the same as the address of our array. The value of our first element, as we know, is 1. So that's what we've already said before. R stores the address of the first element. And what we then see is that the address of the next element, the second one, is 4 bytes higher than the address of the first element. And so this is always incrementing by 4 bytes. And we always have the correct values. So this is how arrays work in C. You take the size of the data type, you take the amount of elements, you multiply those, that's the amount of bytes you want to reserve. And they're always stored consecutively in memory, they cannot change in size. Next, we will discuss a string in C. Strings in C. We do this at this point simply because a string is a special version of an array. strings and arrays are very, very, very similar. Because what is a string in C? A string in C is simply an array of char types. But with one small exception, we end a string in C always with a null byte. So it's not only an array, it's an array of chars plus one extra char to terminate the array. Let's look at this code. This first line of code in the main function, it creates an array of chars ABC. This is not yet a string. This is simply an array of chars ABC. The second line, however, this is a string. This stores the characters ABC in an array of chars, and the null byte. So this is how we can write the null byte as a string literal, as a char literal. And writing this char ABC2 is exactly the same as writing this third line. These two are exactly the same. Okay? Now, why do we use this null byte? Well, we will show you by example. So for that, we have printed these three strings, of which only two are correct strings and one is incorrect. We print all of those and keep in mind a little bit the memory layout here. So let me open the slides real quick and we go to strings. Here's our memory layout. Our three variables. So what has happened? For ABC1, we need to reserve 3 bytes. What will our compiler do? In practice, it will reserve 4 bytes, 1 word, and it will store these characters there, ABC. Now, for ABC2, we reserved 4 bytes. As you can see, it's 1 byte larger. So we write the 0 byte here, and then ABC3 is exactly the same. Okay. The value here, at those question marks, we do not know what this value is. Because we haven't written to that. We just reserved it. It contains some random bytes. Now once we execute puts, it will print a string to the terminal. That's what puts does. It's a very bad way of doing this, but we will show you what will happen. Strings.c, strings. Let me show you first the output, and then we can discuss this. So what we see here is that puts ABC1 seems to output ABC, which is very strange. But this is because when you print a string in C, what you will do is you will give the memory location of the first letter of the string, and then you will simply advance your memory pointer by 1 to go to the next character in your string, and you keep doing that in a while loop until you encounter the character, the null byte. Then you know the string has ended. So if we print ABC2, we will start here at A, we print this character to the output, then we go to the next memory address, this will have B, we print, we go to the next memory address, C, we print, next memory address, the null byte we know to stop. But when we printed ABC1, there is no null byte, so it's after this one, after this printing C, it will just go to the next memory address. Well, what's being stored in the next memory address? Because we declared this array as well. Well, this array is stored in the next memory address. So, puts ABC1, prints ABC, and only stops when it encounters the null byte of ABC2. And we're lucky we're storing a null byte so soon after we declared ABC1, because if not, this could have printed half of our memory, right? It will print until it finds a null byte. So, when we declare a string, or when we think about strings in C, always remember to include the null byte. And that's also the difference between the length of a string in C and the size of a string. It's not the same. The size of a string is always 1 higher, the size in memory, than the length of your string. This string is length 3, size 4. So we can see this already right here when we print the size of. So our incorrect string was size 3, our correct strings were size 4, and they all have these addresses separated by, should be 4 bytes. That's how strings work in C. Special variants of arrays. The last data type that we're going to introduce are structs. So structs is C's way of letting people manually declare data types. You can make your own data type, and you do this by combining other data types. So just like an array is a collection of multiple elements of the same data type, in this way a struct is a collection of multiple variables of different data types. All of these variables will be placed behind each other consecutively in memory and can be addressed using the original struct pointer. So, for example, a struct person is being defined here. The struct contains 3 fields: an integer age, a char, a pointer to a char, right? And a pointer to a char, we can store the address of the first letter of a string in that. So that's what we're going to do in this struct. We're going to store the address of the first letter of someone's first name in memory, and this will be a 0 terminated string. So we store 2 addresses and an integer in the struct person. We now instruct the compiler whenever we want to create a person, please reserve enough memory to store all these fields. So that's what's happening in this code as well. This line 10 defines a new person P, and it reserves on the stack enough memory for this person P, for all of these 3 fields. And if we print the size of the struct, we're going to figure out how much space we need to store all of these. Now, if we do this manually, we might count like this: 4 bytes for an age on my machine, 8 bytes for first name, 8 bytes for last name. But as you can see here, I've already compiled it. Let me execute it again. So as you can see here, the size is 24, while 4 plus 8 plus 8, that's only 20. The reason that it's 24 instead of 20 would be the minimum, but it reserves 4 bytes of padding as well. This is done simply for low-level optimization reasons, but sometimes in between fields, empty space is being left open. So behind this int, there will be 4 bytes of padding reserved. If we would declare 2 ints, this would not happen, and we would also have 24 bytes. This has to do with processor optimizations. I'm not going to go into detail, but just know, minimally, the size of the struct will be the sum of the sizes of its elements, but it's not always exactly the same. There might be some empty space in between the fields. So this struct is 24 bytes in size. You can see in the output. How can we use a struct? If we simply have the struct reference here, the P refers to the struct that we reserved, we can use the point operator to access any field of the struct. So then we of course put the name of the field. So this assigns 54 to the age integer. What this line of code does is a little bit more special. So this James string, so we define this, and whenever we compile the C program, the compiler is going to look for all strings that are defined. There are multiple here, and it's going to put that in a special part of memory. When we define p.firstname equals a string, well, we can't really store a string in a struct, but we can store an address that refers to the first character of the string. So that's what happens here. This string is being created the moment we start our program. It's being placed in a special section of memory, together with all of the other strings. And what happens here is we save the address of that string to the first name field. The same goes with the last name field. So that's what happens here. And then we can print all kinds of information. So the size of the string, the size of the struct, sorry, is 24, as we checked before. And then we have the address of P, simply the address of the struct, which is reserved, the memory is reserved somewhere on the stack. we can print the address of the H field, and since this is the first field, it's going to be the same address as the address of P. We can see this here. And then we print the address of the first name and the last name string. And you see a very different address here. It's not even close to the address of the struct. And that's because of the reason I just told you. First name and last name are being placed somewhere in memory in a different section. And by printing p.firstname, we are printing an address because first name is an address. It's a pointer. And the address is referring to that section of memory where all the strings are saved. So what you can see is that first name and last name are both stored next to each other in memory, but it's a different section than the stack, where the person P is being reserved. As a last step of this crash course, we would like to introduce you to function calls in C. So a function in C can simply be declared. We already used the main function in the different examples. Now we define another function called factorial, or FAC simply. And so first you define the return type of your function. You can only have one return type. In this case, it's an unsigned long, a long that's always positive. And then you can give an argument list. I have provided one argument here. You can provide multiple arguments, comma separated. Very similar in all languages. This is how you define a function. Return value, function name, argument list. This function is a recursive function, meaning it calls itself, and this function simply calculates the factorial of n. So how does it work? If n is 0, factorial is obviously 1. If n is bigger than 0, well, the factorial is n multiplied by factorial of n minus 1. This is a simple recursive function definition of a function that calls itself and eventually will resolve to the factorial of n. So what else can we see in this example? We can see the use of scanf. So you declare an empty integer n, and then we print to the terminal, enter a number, and then we ask the user for inputs with scanf. We give the address of n to scanf, meaning we want the result of the user inputs. The format, we say, is a number with %d, and we want the number results to be stored at the address of n. So after this line of code, whenever a user inputs a number, it's being stored in n. This is how you do user input in C. If n was negative, we exit with an error code. If not, we execute factorial of n and we print that result. Let's quickly compile this. And let's run, and you see we have to give a number. Factorial of 5 is 120. This is a simple program simply to illustrate how you can call a function. The result is being used directly here. You could store the result in a different variable as well. That was it for the crash course of C.